Welcome to this executive briefing on 5G mobile networks. I'm Ross Bagurtis. 5G has a wide variety of meanings, and the intention of this briefing is to focus on the technical aspects of 5G mobile networks. I'll break this down into four areas. First, what's driving the need for 5G, and what are the limitations of our current LTE infrastructure? Next, the ITU, or International Telecommunications Union, has developed the objectives for 5G, so we'll briefly take a look at what those objectives entail. Then we're going to examine the technical design goals of 5G based on those ITU objectives. And last, we'll spend the most time discussing the technical implementations of 5G networks. Let's get started with the need for 5G. The quantity of devices being added to the LTE network is growing rapidly. For me personally, 10 years ago, I had a single device connected to the mobile network. That was my smartphone. Today, I have three devices. I have a smartphone, I've got my watch, and I have a tablet. And I'm not alone in this. As technology becomes smaller, more affordable, and capable of connecting to a mobile network, consumers are going to buy these devices and connect them to the networks. Additionally, the content these devices share is becoming more data intensive. Photos are becoming higher quality, meaning larger file sizes. Sharing movies is now commonplace, and new applications are continuously being developed that require large amounts of data to be transferred quickly. The LTE network can only accommodate so much device growth. And with LTE, additional radio channels are required to add more users. Higher capacity backhaul networks are needed to move traffic away from the RAN, or radio access network, to the internet and back again. And all of this is expensive. We will see that one of the design goals of 5G is to be more efficient with the resources currently available. And it's not just consumers that are going to drive the need for 5G. One of the most talked about technology advancements that requires 5G networks is self-driving vehicles. Self-driving vehicles will require a low-latency data network with the ability to provide quality of service, or QoS. QoS is a method of prioritizing network traffic. In this case, QoS would provide a very high priority to vehicle communications and provide a much lower priority to something like streaming video traffic. This way, vehicles can communicate quickly to prevent collisions, while a user streaming a video would likely not even notice a brief network delay while viewing, as videos typically buffer content for smooth playback. Today, LTE is unable to provide this quality of service feature. Additionally, businesses have a need for next-generation mobile networks also. In the retail and restaurant space, augmented reality on smartphones could offer special discounts to a user when they are near a business. Artificial intelligence voice assistants will have lower latency access to the network, making suggestions based on location data and user requests much more efficient and effective. Manufacturing, healthcare, and other verticals will also have a whole new set of needs based on massive IoT device deployments. Now, IoT is the Internet of Things devices. These are oftentimes associated with home automation gadgets like light bulbs or home security cameras. In a manufacturing plant, these IoT devices take the shape of sensors and controllers, and when deployed on a massive scale, will require a high-speed, low-latency, reliable network to feed data back to an artificial intelligence system that can then provide feedback for efficient plant operation. So there are whole new markets that 5G can accommodate based on the design objectives of 5G, something that LTE cannot currently do. One of the reasons LTE cannot accommodate the requirements is that LTE is not a low latency network. Now, latency refers to the amount of time it takes a message to leave an end user's device, reach the intended network target, and return again. One of the issues with LTE deployments is reaching the internet from a user's handset requires moving traffic to a regional point of presence, or POP. This allows mobile carriers to count the data so the user can be billed accordingly, as well as remove header information from the messages used to move it through the mobile network, which are not required and actually not desired to move traffic across the internet. For example, if you're using one of the large mobile network providers and you have your smartphone in, say, Denver, Colorado, when you connect to Pluralsight.com on your smartphone, your traffic leaves your device, is sent to the cell site, then back over a backhaul network to the regional point of presence, or POP. In this case, it's going to be in Dallas, Texas. And then finally to the internet. Then it can reach Pluralsight.com and make the path back again. The traffic from your smartphone has to travel hundreds of miles from its source just to reach the internet, and then take the same path back again. When you are directly connected to the internet, like at home or in an office, network traffic typically doesn't have to make this expensive trip across the country to reach the internet, making these communications have much lower latency. If a cell site could have its own internet POP, access to the internet would be more effective in several ways. First, the cost of moving the data would be reduced, as you do not require expensive backhauls to a regional POP. Additionally, access to the network resources would be much lower latency, as the traffic wouldn't have to travel hundreds of miles back and forth again just to reach the internet. 5G mobile networks require this low latency and therefore require rethinking how the internet is delivered to the cell site. 5G, along with another technology called multi-access edge computing, or MEC, will allow this to happen. And although this briefing doesn't cover MEC, there's another briefing that will cover this exact topic. For now, let's get back to 5G. Now that we have a general understanding of the need for 5G and a few of the limitations of LTE, let's take a look at the design objectives outlined by the ITU. The ITU has outlined 4 broad objectives for 5G. First is service awareness. This is the technical component of 5G. It outlines speed and latency requirements, security, growth, energy efficiency, among other things. I'll discuss this criteria in more detail shortly. Next is data awareness. This objective is referencing the large quantity of data being created by the end users and the devices, like pictures, movies, or sensor data, as well as the data available on a local network or the internet. Having high speed, low latency, highly reliable access to this data is critical for next generation technology to operate correctly. The next 2 objectives are much less technical. Environmental awareness focuses on energy efficiency and optimization of the technology. Powering a cell site is expensive, and there are tremendous cost savings to be made by making more efficient use with power. Making these systems more efficient and optimizing resources means less electric use, meaning lower power bills for the cell carriers, as well as being sensitive to global environmental awareness. The last objective from the ITU is social and economic awareness. Access to the internet is critical to the success of an individual or a culture. This objective is asking that organizations be sensitive to providing network that is accessible to as many people as possible, and so that the cost is not prohibitive to use. You should see with these design objectives from the ITU that 5G is bigger than just creating a high-speed, low-latency network. The objectives are designed to account for a changing global network, improving efficiency, and bringing mobile networks to more people and business verticals. There is amazing opportunity worldwide for providing a quality, high-speed, low-latency mobile network. Let's move on to the more technical aspects of 5G. The ITU set the general design objectives for 5G, and then another group, the 3GPP, or Third Generation Partnership Project, has been using those objectives to create realistic technical design goals. These goals align with what hardware manufacturers can actually build, as well as set some milestones which will allow mobile carriers to deploy 5G technology alongside LTE networks, helping to reduce rollout costs and allow engineers time to finalize hardware designs that meet the goals of the final specification for 5G called the IMT 2020. 2020 here is referencing the goal to have these designs completed by the year 2020. Let's take a look at some of the important features of these technical goals. The first major and likely most important design criteria is for speed and latency for 5G networks. The guidelines state 5G networks will allow a user to enjoy a download data rate of 100 megabits per second, with some types of communication able to reach speeds of more than a gigabit per second. Additionally, the latency on the network will be less than 20 milliseconds, with some applications demanding ultra-reliable, low-latency communication, or URLLC. One of these applications is self-driving vehicles, which will require latency of less than a millisecond. The second feature is to provide for secure and reliable communications. Because of the new uses for 5G networks, it's paramount that the integrity of the data passed on the network is maintained. Tampering with data on the 5G network has the potential to cause accidents with self-driving vehicles or have catastrophic consequences in a manufacturing plant using massive IoT devices to collect information used to make decisions about plant operations. It's critical that this information be secured. A third important design feature is for future growth. As discussed earlier, the quantity of devices connected to the network will grow, as will the demand for bandwidth. The specifications for the rollout of 5G allow for the use of existing LTE technology to bring the first generation of 5G networks online, and then eventually migrate to a standalone 5G technology, which doesn't require the use of LTE. Additionally, the 3GPP group has set some milestones to allow for the gradual rollout of the technology, which will ramp up the ability to accommodate new technologies over time, instead of having a giant leap forward, which is both expensive and unrealistic based on currently available hardware. The last important technical design feature is for energy efficiency. Powering a cell site is expensive. Adding more capacity to a site will ultimately result in greater power usage. The engineers designing the hardware will make use of several technologies to reduce the energy footprint for delivering 5G networks. And now that we have a general understanding of the design goals of 5G, let's move on to the more technical components of 5G networks. To deliver the speed and latency requirements of 5G, engineers are developing equipment that will make use of several technologies. Let's take a look at 5 of the most important technologies. We'll examine millimeter waves, small cell deployments, massive MIMO, beam forming, and full duplex communication. First, in order to deliver wireless communication, we need a piece of the electromagnetic spectrum. Some of the spectrum is divided into channels, and these channels are regulated by the FCC in the United States and by other regulating bodies around the world. In order to make use of these channels, carriers must pay the regulating bodies a fee for use, as well as work with a limited spectrum of usable channels. Today, carriers use microwave bands. If we take a look at this chart, you'll see that we start with ultra-low frequency bands on the far left, and then it moves into ionizing radiation on the right. Moving from left to right means the wavelengths become smaller and smaller. Right where this line is, that's where most current cellular technology operates. And if we move over to the right just a bit, we have millimeter waves, which exist much closer to the infrared spectrum. The most enticing feature of millimeter waves is the tremendous availability of channels in this spectrum. This is a huge benefit for mobile carriers. However, this comes with a challenge. Millimeter waves have difficulty traveling through objects. If we take a look at the scale of waves again, the ultra low frequency waves, those are generated using an antenna that's a mile or more long. And these waves can easily penetrate objects, whether it be the earth or water or something else. This technology is used to communicate with submarines because it can easily travel through objects. However, if you consider the visible light spectrum, we can easily recognize that light waves have extreme difficulty penetrating objects, which is why we see shadows. The waves just longer than visible light are infrared, and just longer than that are millimeter waves. TV remote controls make use of infrared waves to send a signal to your TV, and if there's an object between the path of the remote and the TV won't receive the signal from the remote. Likewise, millimeter waves, being very close to the infrared spectrum, also have difficulty penetrating objects. And the additional challenge of millimeter waves is the range, no more than a kilometer from the source. So we have this short range and difficulty traveling through objects. There's two ways we can combat the limitations of millimeter waves. One of the solutions is to make the cell size very small and deploy a large number of radios and antennas in order to provide the necessary coverage to an area. This is a somewhat simple solution. However, it introduces yet another problem. When we introduce a large number of radios in a location where there are buildings and other stuff for the signal to bounce off of, we end up with signals coming from many different directions, which has the potential for creating interference. So although the small cell size will be a benefit to 5G deployments, there are some additional challenges to overcome. This is where the next few solutions come into play, which are all actually pretty nifty. Using multiple antennas, one can mathematically calculate the direction a signal is coming from, its strength, and the location of the device sending the signal. It can do this even if there are buildings and other objects in the signal path. Moreover, that same math can be used to generate a signal using multiple antennas to direct a high-powered signal directly at the sending device, reflecting the signal off of buildings and other objects as necessary. This is really interesting technology and allows for some significant steps forward in mobile wireless technology. What I'm talking about here is two separate technologies which work in conjunction with each other. One is called Massive MIMO. MIMO is really just multiple input, multiple output, and means using many antennas to send and receive signals. By using multiple antennas and some mathematics in the processing of the transmit-receive hardware, we can actually create directed beams of signal, boosting the signal where it's needed and canceling out the signal where it's not needed. This is called beamforming and is the second technology used to help make millimeter waves more effective. By creating high-powered beams of signal directed at the intended device, millimeter waves can be more powerful and send a stronger signal to the devices that need them. Now we can use both Massive MIMO and beamforming in waves besides millimeter waves, and 5G will likely do that with existing channels in the microwave spectrum too, the ones we use now for LTE. However, because of the nature of millimeter waves, Massive MIMO and beamforming can help enhance the performance of those smaller waves. However, I'd like to be very clear about millimeter waves. Even with Massive MIMO, small cells, and beamforming, millimeter waves still do very poorly when penetrating objects. What this means is if a user is inside of a building or in the shadow of a signal, the signal will drop off quickly, as will communication between the device and the cell site. An option to solve this is to use a femtocell. This technology is currently used for customers who are in an area of poor cellular coverage. A femtocell is a small radio deployed inside of a building and then typically connected to a high-speed internet connection. The femtocell device builds a connection over the internet to the carrier, and then a customer's handset will connect directly to the radio in the femtocell. It effectively extends the carrier's network into a building. This could be real useful for 5G and millimeter wave use. However, it may not be ideal due to the extremely large number of femtocells required to provide coverage inside of every building where coverage might be needed. Because of this, it's likely that current microwave channels used in LTE today will continue to be used in 5G deployments in order to accommodate users inside of buildings. However, millimeter waves will be useful in outdoor deployments, especially in cities where there are dense populations and lots of buildings. Small cell sites mean that the available channels can be reused in an area that's more than the range of that signal. For example, if a millimeter wave channel can only travel 1 kilometer, then you can reuse that same channel in a radio that's more than 1 kilometer away. This means that a carrier can reuse the channels and have a broader deployment, allowing for more users. Another technology which will be used in 5G networks is to be more efficient with full duplex communication. Now, understanding duplex is actually pretty simple. Imagine the walkie-talkie you may have had when you were a kid. When you and your friend were talking to each other, one could speak, the other could listen. If you tried to speak when your friend was speaking, this just shut down the communication and no messages were received. This is called half duplex communication, meaning only one signal could be sent at a time. The telephone, on the other hand, is full duplex. When you use the telephone, both you and the person with whom you're speaking can talk at the same time. Now, this may make conversation challenging for a human. However, with networked communications, being able to send and receive data on the same channel at the same time doubles the use of the channel, making for more efficient communication. In current LTE technology, we do use full duplex. Well, kind of full duplex. It's implemented using FDD, or frequency division duplexing. The way this works is one channel will be used for the downstream communications. These are the communications that come from the tower to the user's handset. So when you're surfing the web on your phone, and the information coming from the internet to your phone will use one channel, say channel A. Then the upstream communication from your handset to the tower will use a separate channel to send this information. So in the case of surfing the internet on your phone, you may fill out a form or send a text to a friend, and in this case it will use a separate channel for the upstream communication, say channel B. This way you can both download and upload information at the same time. Maybe you're listening to a podcast while texting a friend, and your handset will seamlessly transmit and receive at the same time. However, FDD requires 2 channels to provide this full duplex communication, and each channel can only send or receive information. This is terribly inefficient, and the reason we are creating full duplex communications here is we're using 2 half duplex channels. The upstream channel can only send data upstream. The downstream channel can only send data downstream. Doing this creates inefficiency. A user handset has limited need for sending data from the handset to the radio. Text, photos, forms, and the protocol overhead from sending IP traffic to and from the internet are all relatively small compared to the amount of data downloaded to surf the web, browse streaming videos, or examine rich content on social media sites. So to use FDD, 2 communication channels are being provisioned, and only one of them is being used to its full potential, leaving the upstream channel in light duty mode. There are other options to allow for full duplex communication to be used in a single channel. This is done by creating separate time slots for upstream and downstream communications. This is called time division duplexing, or TDD. With TDD, we no longer need a separate upstream and downstream channel, and instead can take the 2 channels used in FDD and now use each of them as both up and downstream, effectively doubling the capacity and creating massive efficiency gains. TDD works by quickly switching between sending and receiving data. However, this happens extremely quickly, allowing data to effectively be both sent and received simultaneously. Additionally, using TDD along with Massive MIMO has additional benefits of scalability. TDD with Massive MIMO allows a carrier to deploy more antennas to accommodate more handsets or other devices. Research done by Emil Bjornsson, Eric Larson, and Tom Marzetta, all experts in signal processing and MIMO, discovered that using TDD and Massive MIMO, you can add as many end-user devices as needed as long as you add more antennas to accommodate this. And this is something not possible with FDD. And in fact, you reach a limit where adding antennas to the MIMO system no longer accommodates more end-user devices in FDD. So I just discussed 5 technologies, which all work in conjunction with each other. 5G will make use of millimeter waves, small cells, Massive MIMO, beamforming, and TDD full duplex communication to deliver services to users and accommodate the needs of the next generation of devices and technology. Initially, this 5G will be rolled out on top of current LTE technology and incorporate some of the features of 5G, but not all of it. The first generations of 5G networks will likely be able to offer high-speed connections. However, reducing the latency on 5G networks will require using another technology like multi-access edge computing, or MEC. Sometimes this is called edge computing. And there will be an executive briefing that will focus exclusively on MEC and how that technology will be used to improve network performance. 5G is a mandatory upgrade of mobile networks to accommodate next-generation devices. As I discussed, the ITU has designed standards to build the next-generation network, and the 3GPP has been tasked with the technical design to achieve these goals. The ITU, 3GPP, hardware manufacturers, and mobile carriers will all work together to ensure the success of this next generation of mobile networks. We've covered a lot of information in this presentation, and I hope you found it useful. Thank you for joining me, and I look forward to seeing you again.